These notes are about radical expressions and how to simplify radical expressions. First of all, what's a radical? This first example should be somewhat familiar. The square root of 9. That is a radical expression. You can see the radical symbol over 9. Now, what does the square root of 9 mean? That means that we're looking for a number such that when we square it, we get 9. So can we rewrite 9 as something squared? Yeah, 3 times 3. So the square root of 9 is the same as saying the square root of 3 squared. Since 3 squared equals 9, we know that the square root of 9 is now 3. Somewhat familiar. Usually you don't think about it that way. You'll look at that expression, square root of 9, and just know that that's 3. But it's important to think about what it means in order to understand the next few more complicated examples. Somewhat less familiar, but still used, is the cube root. Notice now there's a little 3 right inside that first sort of arm of the radical symbol. We're no longer looking for something such that when we square it, we get 64. Now we're looking for a number such that when we cube it, we get 64. After some experience and familiarity with perfect cubes, you'll know that actually 4 times 4 times 4 gives you 64. So this is really the cube root of 4 times 4 times 4, or the cube root of 4 cubed. Well, if we're looking for the cube root of 4 cubed, that is just 4, because 4 cubed equals 64. Cube root. Let me write that out just in case you've never heard that before. The cube root. So that's what that's called when there's a little 3 in there. Now we have a 4 as that number. That's called the fourth root. You can imagine there's no limit to the nth root that we can take of a number. I can talk about the 6th root, or the 10th root, whatever we want. This problem, you might be tempted to first figure out what is 7 to the 4th power, 7 times 7 times 7 times 7. I don't know, and I don't care, actually, because I know I'm looking for the 4th root of 7 to the 4th. That's just 7, right? Whatever 7 to the 4th was, I don't know, but when we take the 4th root of it, we're just going to get 7 right back, because 7 is the number such that when we raise it to the 4th power, we get 7 to the 4th. So in general, I can talk about the nth root of a number, let's say x. The nth root of x. Let me write that out. Nth root of x. And for the rest of this, these notes, we're going to be talking about definite roots. We're not going to be sticking with unknown roots. The name for that little n, the name for that number is called the index. So the index for this last example was 4. The index for the previous example was 3. What's the index for that first example, the square root of 9? There's no number written in there. Well, think about it. We needed a number such that when we squared it, we got 9. So the index was actually 2. So you might be asking yourself, how come we never write a 2? The answer is that root is so common, the square root is so common that we've kind of abandoned it. Because 9 times out of 10, if you're talking about a root, you're interested in the square root. It's just the most common root, I think, that you see in math. But there really is a hidden 2 as the index there. It's not a 1, it's a 2. Let's look at how we might simplify some radical expressions. Again, we'll start with a more basic example. Let's look at the square root of 48. You might remember from examples like this before that if we're trying to reduce the square root of 48, we want to look for any perfect squares that are factors of 48. Remember, this really has an index of 2 right here. We're looking for perfect squares that go into 48. So let's think about the structure of the number 48. Can we break it down into its factors? I know 48 is 16 times 3. And that's really good that I broke it down like that, because 16 is a perfect square. 16 is 4 squared. So instead of writing the square root of 48, I'm going to write the square root of 4 squared times 3. And now, since 4 is a perfect square, part of this expression is the square root of 4 squared, and I know that that is just 4. What's left over is the square root of 3 inside the house. So we broke it apart into what we could, and the 3 was left over inside the radical. The square root of 4 squared turned into just a 4. That's all we could do, because root 3 cannot be simplified any further. So the square root of 48 turns into 4 square roots of 3. A similar process applies if we're trying to simplify the cube root of a number. Let's try the same thing. This time I'm looking for perfect cubes that are factors of 54. It's probably a good idea to be familiar with the first few perfect cubes. 1 cubed equals 1, 2 cubed equals 8, 3 cubed equals 27, 4 cubed equals 64. Those are some nice numbers to be familiar with. These are perfect cubes, just like 1, 4, 9, 16, 25, just like those are the perfect squares. You're probably pretty familiar with those already. So how could we break apart 54 into some perfect cubes? Actually, if I look at that list we just made, 27 is a factor of 54. 54 is 27 times 2. But 27 is 3 cubed. So I'm going to write the cube root of 54 as the cube root of 3 cubed times 2. Now, part of that expression is the cube root of 3 cubed. That's just 3. What's left over inside the radical is the cube root of 2. I guess the 2 is what's left over inside the radical. That can't be simplified any further because there's no perfect cubes that are factors of 2. So we're done. 3 cubed roots of 2. It's a similar process, but instead of looking for perfect squares, we're looking for perfect cubes that go into the number inside the radical. By the way, that number is called the radicand, the number that's inside the radical symbol. It's a good word to know. Now, let's step it up a notch. Not talking about the cube root of a number anymore, but the cube root of a variable. You might already have an idea of what this is, the cube root of x cubed. Well, what cubed gives us x cubed? Just x. The cubed root of x cubed is just x. It already is written as a perfect cube. So you might be thinking, our goal is to get the radicand, the number inside, written as perfect cubes as best we can. It won't always be all perfect cubes, like we saw in the example of 54, but we want to try to write it in as many perfect cubes as we can. And that way, the cube root of anything cubed is just itself, and it can come outside the radical. Let's look at this next example, the cube root of x to the 5th. Well, x to the 5th is not a perfect cube, but let's see what I can do. I can call x to the 5th x cubed times x squared. Take a moment and convince yourself why that's true. I know that from our exponent properties, if you multiply two numbers with the same base, you can add their exponents. So 3 plus 2 does give us that 5. So I have not changed the problem. I just rewrote x to the 5th as x cubed times x squared. Now look, part of the expression is the cube root of something cubed. The cube root of x cubed is just x. What's left over inside the radical is the x squared. So cube root of x squared is left over. We did the best we could. We simplified it by pulling out an x, because x cubed was one of the factors of x to the 5th. You could argue that this looks less simple than the original, but in fact this is considered simplifying radicals. Notice the cube root of x squared is still there, and there's nothing we can do about it. A couple more examples. Cube root of x to the 18th. This one's really interesting. Can we write x to the 18th as something cubed? We can. We can write that as the cubed root of x to the 6th cubed. Again, take a moment and convince yourself why that's true. Because of our exponent properties, I know that if we have a number to a power raised to another power, I can multiply those powers to simplify. 6 times 3 does in fact give us 18. So x to the 6th to the 3rd equals x to the 18th. Now, what is cubed in the radicand? It's the x to the 6th. So x to the 6th is the cube root of x to the 18th. Think about it. X to the 6th times x to the 6th times x to the 6th does give you x to the 18th. So therefore, if you cube x to the 6th, you're back to x to the 18th. That should make sense on some level. A couple more examples. Now, instead of just x's, I've given you 3 variables to think about. And now we're talking about the 5th root. Remember, we could be doing this with any index. I've just started off with cube root to make it a little more easy. Let's see, our goal is to write things in the radicand as powers of 5, because I know that the 5th root of something to the 5th is itself. Well, x to the 5th is already written as a power of 5. It's our lucky day. Y to the 7th, well, let's see what I can do with that. I can call that y to the 5th times y squared. A couple of examples ago, I reminded you that if you multiply things with the same base, you could add their exponents. So y to the 5th times y squared does give us y to the 7th. Now I have a 5th power of y that I know will help us simplify in the next step. Z to the 20th. That is z to the 4th to the 5th. From our previous example, remember, we can break up powers like that. I know that I can multiply power to a power. And there was nothing left over there. So let's see, what had a 5th power that can simplify? 5th root of x to the 5th is just x. 5th root of y to the 5th is just y. 5th root of z to the 4th to the 5th is z to the 4th. What's left over inside the radical symbol? Just that y squared. I guess I didn't need to make that so big. And we've simplified it. Notice the factors that came outside of the radical symbol were the factors that had the 5th power. And then the y squared was kind of trapped inside because we couldn't simplify it as powers of 5 any further. We're going to end these notes with just one more kind of crazy example. Now I've thrown numbers and variables as part of the radicand. So let's take a look at this. We have the 4th root of 80 x to the 5th, y to the 9th, z. Ooh, we have to do the same things that we've been doing, but now with the number as well as with the letters. Let's break down 80. I'm looking to write 80 as a perfect 4th power. Well, I know 80 is 16 times 5, and 16 is 2 to the 4th. And it might take you a little bit to figure out that 80 can be written as 2 to the 4th times 5, but the more experience you have with these numbers, the quicker that will come. So let's write out what we can. 80 is 2 to the 4th times 5. X to the 5th is x to the 4th times x to the 1st. Y to the 9th is y to the 4th times y to the 4th times y. Could I have written that a simpler way? I know that that's y to the 4th squared times y. So maybe I could have written that in a simpler way, but I think I'll leave it like this for now. Times z. The z had the power of 1. There's nothing much more we can do with that. Let me just separate that off there. Alright, so what can come outside the house? In other words, what is written as a power of 4? 2, x, y, another y, and that's it. What's left inside the radical? The 5, the x to the 1st, a y, and a z. The last thing I'm going to do is just rewrite the y times y as y squared. We get something that looks rather complicated, but it is considered a simplification of the above radical. Notice that we just used all the skills that we talked about throughout this whole video, finally in one example. So you can imagine how these examples can get kind of complicated by throwing a lot of different powers at you, but if you really understand fundamentally what it means to be a square root, cube root, 4th root, you'll be able to break the radicand down into its appropriate factors and simplify. Good luck!